Sound. Okay, we got sound. Top window audio. Do we have audio for the top window? Okay, let's take, so first of all, let's acknowledge just, the situation here. First of all, I don't feel motivated at all. I don't want to do shit right now, but, I don't feel like doing stuff, but I also have the desire to accomplish things, if that makes sense. So, like on a dopamine scale here, I don't have much going on here. But we're gonna try to, like, power through this and get something going. I want to actually see cross sections of the voxel grid in the renderer, so we have something to kind of work with. So before I do anything else, the first thing I want to do is take all of the code from yesterday, and we're gonna move it around a little bit and organize it into just to make it a little bit gather our bearings, and just we're gonna gather our bearings by just organizing stuff a little bit. And I added one more level of indentation here, so instead of 52 characters for my column limit is now 56. So if I go into my settings in my style configurator, settings preferences. I really don't know the difference between preferences and style configurator. Like, after all these years, they seem like the same word to me. Yeah, so my number of columns here is 56 now. My hard limit is 64. But we added this extra level indentation so that we can do some stuff. And what we're going to do is we are going to subdivide things based on what degree the function is. So this main image here, this is the entry point. So this is the 0th degree function. So it is 0 degrees removed from being the main function, right? So we're just gonna give it a whole bunch of zeros, right? We're gonna just use these numbers to, like, mark where that begins and ends. And now we could, like, mark it with, like, degrees removed. But the thing is that makes more visual clutter. I want, like, some type of hard separator where I can actually see stuff. And I want some type of line that is more pronounced than this style of line. So let's look at this, and now let's take anything in main image that's being called and be like, okay, that's going to be a 2nd degree function, right? So right here we have this fragment coordinate to fragment percentage, so that's a 2nd degree. This fragment percentage converting to the ray world coordinate and ray world normal, that is also a 2nd degree function, or sorry, a 1st degree function because it's 1 degree removed. And then SDF render scene is also going to be a 1st degree, right? So now that we've highlighted these in blue, we got to go fetch them and figure out, well, where are you, right? Something I'm noticing here is with SDF render scene, you know, these functions get kind of big, and then we lose track of, well, what is this here, right? So so we might want to make a note of the end of functions somehow, but without being too cluttery is the problem sometimes. So I'm going to use the actual function name kind of like here, like that. And I don't know if that's the best way to go about that, but we need some way to know what that is. Or alternatively, we could do something like we could do we could do something like this, where we have the actual scene, and then we have a description of what it is, right? We could do like a double line like that between the functions. The problem with that is that it can kind of destroy our line hierarchy, where this looks like doubly thick as compared to this. So we're like using up more space. Is that an appropriate solution here? And I don't know. Stylistically, you know, if the equal signs are always used kind of like in twos, and then our lines here with the dashes are used always one thick, I mean, that could help create a better line hierarchy. So, you know, maybe that's a good idea. I don't know. So SDF render scene. You know, I'm just going to go for it because I think that, you know, maybe maybe it'll be a good idea. I don't know. So with SDF render scene, right, that is in our first degree removed. And we'll give some padding here when we have these dividers between the different degrees. So SDF render scene, and let's just keep on going up here and make sure that the functions are kind of like in the correct order here. So we have this render scene, and after that we have this integer modulus, which kind of seems to have just been thrown in there. Let's skip over that, and let's put a breakpoint here at render scene and keep on going. And we're just looking for where's the next thing that has like this blue showing up. So okay, so I found it, and we're just gonna say fragment chord frag chord to frag percent. So that's a basic summary. So basically I want a summary where I'm not being very terse, and I'm not worrying about having a normalization with the name of the function, right? And then when I name my functions, I'm having a very strict naming convention for how that works. But for here, let's just go frag chord to frag percent, and then we can still do FC CTO and then FP like that. And then we can indent that in there. We can take this, we can paste that down there. And basically, we're just going to do some cleanup so that we can get our bearings, if that makes sense. So SFD integer 3D, no, that's interpolate 3D. That's an interpolation 3D. And I see that this is a different function, so let's take this, and this is interpolation 3D, so it's interpolation with three-dimensional points. And then we can do SFD I3D. And then we can take this same line here, and we'll just kind of and I feel like this is a bit bulky, and also it's kind of like extra work, but you know, you only write the code once, so let's try to make it kind of as organized as possible, especially because this looks like it's going to start to get way out of hand pretty soon. So it would probably be best to are we recording here? Well, it looks like we're recording. Well, hopefully we are. If not, I can always grab the recording off of Twitch, I guess. Okay, so frag chord to fragment percentage. This interpolation 3D, we can take take the line from here, paste it over here, take the line from over here, paste it over here. Okay, interpolation 3D. That is some other degree of function. But these are highlighted, so I know they are the second degree or the first degree functions. So first degree removed functions is what I mean. So this is frag percent or frag per to camera array. That's basically what it is. So ray world coordinate and ray world normal, that's basically a camera array, right? Those two components. So so FP, CTO, RWC, and RWN, right? Okay, and now that we have that, we need to actually indent one more. So we're getting kind of crazy with the indentation, but the idea is that we're not excessively indenting. We're kind of like using the indentation to, rather than just indenting for scope, like you'll see in a lot of code, we're also indenting for other things, right? For like section headings and whatnot, just to make it a little bit easier to traverse through this code. So let's take this, and you know, as we do this kind of excessive indentation, you know, we'll start to like, you know, oh god, our diagram here is outside of our column limit. That's no good. So, you know, some of these comments need to be fixed up a little bit, and that's kind of the problem with this kind of like meticulous indentation, is we start to you know, just lose that real estate. But that's the thing. That's why we want to like, that's why we're trying to keep things as terse as possible, and try to we're just trying to be very clean about it, be very meticulous with our indentation, be as terse as possible. And in order to encourage the terseness, that's why we have such a strict indentation limit here. So this RWN doesn't really need to be indented like this, but I see that it's probably indented to line up with this. So what we can do for some things, if the comment was like, oh, that comment's like way out there, we can say, we can offboard that comment. So positive Z is further back into screen this way to help normalize voxel grid. Okay, so what we'll do is positive Z moves, positive Z dives into screen, right? And that's kind of like a, you know, maybe not a technical term, but it's enough for me to like know what the hell that means, right? So when we look at extracted block comments here, we can extract that and say positive Z dives into screen, right? We can take that comment, and then we can just paste the original text for that. And the reason why we're going to just offboard our comments like this is because I do believe that the hypothesis that comments are the last thing that are read, right? And I think comments are very important for code, but I also do agree that they are the last thing that's going to be read. It's the thing that people kind of read. Like, after everything else has gone wrong, people will read the comments, right? So we might as well just kind of like chain together a section of different comments, right? So we'll have hashtag and then the comment block identifier and a hashtag comment block identifier. So we can double click this, and if we want to go to where that is actually happening, we can just find it again, right? And so extracting those comments can make the code a little bit less lengthy here. So here, polygon and 3D space to serve as the phosphor surface of the CRT monitor. Electrons will be projected onto this. Could possibly use a matte 4D for this. So as I'm doing this math, I kind of realized that A, B, C, and D, that strangely looks like a 4x4 matrix, right? Like, you know, we just need like one other component here, and then we could have a fourth column, you know? And I know with transformation matrices for like the model view and like the world space matrices, or is it model view? No, it's like view space, eye space, camera space, something like that. I don't know exactly what it is, but they have like these matrices. I think they're 4x4, and so it's interesting that my source code definitely kind of looks like there's a 4x4, and you have to think about it that there's a minimum amount of information you need to do like any type of transformation of data. And that means that even though I'm not using matrices because, oh, okay, I don't quite understand them, my half-baked solution to just like create this plane out of 4 points in three-dimensional space and then just interpolate between here and here, here and here, and then draw this plumb line between here and interpolate between here to get a point on that surface. Well, that is kind of that is my hackish way of creating a plane that represents the screen and putting that plane in three-dimensional space. That's my hackish way of doing that mapping. And you have to think that even though it's a hackish way, there's still a minimum amount of information you need to express any type of transformation of data. So therefore, even though this is a hackish way to get the job done, because it does get the job done, you can start to see the parallels between that and a matrix because, you know, if you're trying to, because there's, it's not that there's only one way to do things, it's that that when you do something with the minimum amount of information required, you're going to start to see that parallelism. Does that make sense? I don't know. But let's take this. This comment kind of doesn't make sense, so what we're going to do is summarize this and what we're really doing is find point on screen plane. So that's really what we're trying to do. We're trying to find point on screen plane. So that's just, this hashtag is just a little comment so that I can find that later. And then what we'll do is we'll go over to our documentation section. We'll do find point on screen plane. And then we'll just paste this here. And then we'll take the same stuff. We'll take this, we'll put this down here. And okay, so with this, screen Okay, so the thing is, we kind of have like this bad terminology going around here, but basically, when I'm talking about the screen plane, I'm referring to a polygon in space that serves as this phosphor surface for a CRT monitor. Uh, Polygon in 3D space to serve as the phosphor surface the CRT monitor electrons will be projected onto. Original comment. Um, okay, so we have the original comment, and then we have more information in retrospect. Okay, so screen plane is also known as CRT phosphor, or FO for short. This is a plane put into 3D space that represents the pixels of the client viewport, also known as the physical monitor. So if you don't know what I'm talking about, it's because I'm using horrible terminology. But if we look at, let's look at ray marching Wikipedia, and see if we can find the diagram for volume ray casting. Not exactly what I was looking for, but let's see if we can find ray marching Wikipedia. Okay, I can't find it on Wikipedia. Can we just find the diagram? There's like a good diagram somewhere on Wikipedia, and I'm kind of looking for it. Can't find it. Let's look at images on the internet, because somebody's already done this. Oh, okay, so en.wikipedia, and this is ray tracing. Okay, so I guess, yeah, that makes sense. So, I mean, ray marching is still kind of like ray tracing in the way it's done. So, if we look at, okay, so I found it. So it is this guy right here. So this diagram right here, this image here with the pixels, these are the actual screen pixels, and this plane is actually going to be positioned in three-dimensional space, and the camera is going to be in three-dimensional space, right? And we map each one of these cells on the image plane onto the screen. So this image plane I sometimes call the FO for the phosphor surface, because I'm using like a CRT monitor analogy where like this is like your electron gun. It's not the best analogy, but I need kind of like a better name for this thing here than just calling it image. I mean, image plane might work, but as long as we know what we're calling it. So I'm going to take that, and I'm going to, from this diagram, and this diagram is pretty long, so we're going to try to see if we can make a tiny URL for this. So www.tinyurl.com, and well, let's take a look at that. How stable is this? How stable is that image going to be on Wikipedia? Like, open link and new tab. I mean, file raytracediagram.svg. I don't see any reason why that name would change in Wikipedia. So we're going to hope that that's a relatively stable link, and we're going to put that in there, and we're going to call it I'm going to call it image plane. And that might actually be something. So let's just do that, see if we can get it. Nice, so we have image plane now. So I'm going to take that, And I'm going to put it in the comments. Okay, so now that we have that, we have a way to like have a diagram for what we mean. So let's go back to this. Okay, so that looks all nice and cleaned up. Now we can add some more comments here. Ray world coordinate, and this one is Ray world normal, right? So one is a coordinate and one is a normal. Okay, and with that, I keep on trying to save. I don't have this saved anywhere yet. So this first voxel query needed, it doesn't have anything. Okay, so these are our first and second. So I'm going to take these, well, not first and second. These are our first degree removed functions. And render scene is also there. Okay, so we're going to paste this down here. And so now it's nice because we got these nice big blocks that kind of like separate the different sections of code. I do like that. Now the next part of what we're doing is let's save this as, I'm going to save this as SDF009. And I'm going to copy it all, and I'm going to paste it into the shader and make sure that I haven't like done any weird like mistake where I've like edited the syntax. And it looks like somehow I've fucked up the syntax here. So I see that as I was extracting comments, I did something very stupid. And if we look at here, right here, that is pretty stupid. It's still a comment, even though I have a hashtag. We still need to put a comment character there, right? So let's take that and let's try to run that, and that is still running, so we're good there. So from here, what's another way we can kind of more appropriately organize this? So not only are these functions here the first degree removed, so the ones that are highlighted in blue, these are first degree removed functions. But there's also a very explicit order to how they're ordered here. So how should we organize that in a way that makes sense? Like what? So I'm trying to enforce a stricter ordering than is required, right? So the ordering we are doing, first of all, is a C-style ordering without forward declarations. That's why main image is the function all the way on the bottom, because it depends on everything else, so everything else must be declared beforehand. Now, I don't know if that is a specific rule of GLSL code. So, like, if we take this function and we go all the way up here to the top, right, and we just like paste it right here, will that not compile? So let's take that and see if that is a constraint, and that is a constraint. So let's see what it says though. V2 is a syntax error, so but that error isn't about the function ordering. That's about the defines here that I used to keep all of my type declarations nice and normalized, so vec4, vec3, vec2, float, and integers. So let's move this function down a little bit, and let's try to just save that and run that and see if that runs, or if there is some type of ordering constraint. And it's still red, and let's see what the mistake is. So let me just scroll here so you can kind of, well, I kind of botched that screen, didn't I? Because I have this like SDF. I have the big advertisement kind of like in front of it. So maybe I should change that. I'll just tell you what it says, I guess. So RWC and RWN, undeclared identifier, and RWC and RWN, syntax error. Okay, so now it's complaining because some of the structs don't exist. So we're going to take this function, and we are going to put it underneath the structs and all these defines. So here we got these defines, and then we have our struct section, and we're just going to try to paste it here. So kind of like we're going to paste it as the first function and see if there is a mistake in the compilation. I just want to see how strict the compilation is just from, you know, trying it out myself. So FP... So there's... Okay, so there's definitely problems here, and nothing that you know, that's kind of what I'm expecting. Let's move it somewhere else. So let's go all the way back down to the bottom again, and not in our comments section, but right here where it was originally. We're going to take it, and we're just going to paste it again. Make sure that we haven't accidentally messed anything up. Still runs. And we'll take this, and we've created this first degree of separation area. Or we did, kind of. I don't see the other straight line of ones. Okay, so we're going to take it, and we're just going to put it in front of something that it calls. So we're just going to, like, split this open really quick, and we're going to put it in... We're just going to put the main function in front of a single function that it calls, and see if the declaration order is kind of like a C-style order. And that looks like that is the case, so... Yeah, okay, cool. So, without any forward declarations, and I don't even know if you can do forward declarations in GLSL code, but without any forward declarations, you have a strict ordering constraint where if you are referencing a token, it needs to have been declared previously. So this function needs to have been declared previously if it's going to be called, and that's why our main function needs to be the last function. So that's why it's on the bottom. Okay, so that is good. I like that, and we're not going to add any forward declarations because by having this kind of strict ordering constraint, it forces a more... Like, there's an infinite... Well, there's not an infinite, but there's a factorial number of permutations when you think about all the different ways you could shuffle this around. It's combinatory logic, right? So, it's like if we have 5 functions, the combinatory logic, I believe, is 5 pick 5, I think, is the logic. I think that's how you say it. So 5 pick 5, or it could be 5 choose 5. 5 choose 5. 5 choose 5. Okay, so it's 5 choose 5. So it looks like 5 choose 5 is not a permutation, but it's a combination. So the difference between a permutation and a combination is that with permutation, the order actually matters, but with combination, the order doesn't matter. So a combination lock is actually a permutation lock. So if we go over here, I'm just going to make a note of here. So for 5 choose 5, 5 choose 5. 1, because choose is a combination, not. Okay, and then we'll do like 1 choose 1, and we'll just kind of cut and paste for like 2 choose 2. And we'll go all the way up to 5, right? And that way I can kind of like remember this later. So permutation, how to phrase a permutation is kind of what I want. How to phrase a permutation. how to say a permutation. And also say permutation, phrase permutation, permutation, say. So basically you want to know the how to, okay, so there's a little statistics thing here. So I'm looking on the internet right now and seeing what kind of stuff I can find here. So let's look at here. So permutation, combination, and derangement formula. So I don't know what derangement formula is. Combinations. So 5 choose 3, 4 choose 2, etc. Permutation formula. So does permutation not have the aspect of being able to choose? There are two permutation formulas. One which you choose depends on whether you have repetitions. For repetitions, the formula is... for repetitions, the formula is n factorial. For no repetitions, the formula is n factorial divided by the factorial of n minus r. Yeah? They're still in the hospital. It looks like they have diabetes.
Oh, they've been diagnosed?
Yeah, pretty sure. Yeah, they had an insulin shot.
Do they know when they're getting out?
I don't know. They haven't texted me back. I called them earlier today.
I think their phone might be out of battery.
Okay.
Can you Facebook message them and ask if they need their charger?
I don't think their phone's out of battery because I packed their phone charger with them, so... I packed their... Yeah.
God, you're good.
Well, no, they asked for it.
Oh, okay.
Yeah, I just packed that into a crate. Yeah, so I'm pretty sure
so...
they're... Okay, and also I called them from the hospital number. I didn't call their phone. I called the hospital to get a hold of them. So, yeah. I think I'm expecting them to call back. Or something. Yeah.
Okay. When you talk to them, would you ask them to call me? Because I've tried a couple times.
Okay, yeah, when they call back.
If it's not too much for them, I mean, if it's too much, that's okay.
Okay.
But I would like to hear from them.
Mm-hmm.
But, totally, it's only if they want to.
Okay. Alright.
Thank you.
Yep. Okay, so let's see. If we look at,
Can I borrow my phone? I want to text Chloe that Frankie's okay. Maybe I should just call her.
Okay.
I'm going to try to, wait.
Okay. Right.
Let me think. What time is it? Does she have, she does not have school.
Alright. Well, I need to keep on going here.
I'm sorry. I'm going to bring the phone back down.
Okay. So, let's see. So, this is the permutations we have for if we could arrange our function declarations in in any order, or not our function declarations, but if we could write our functions in any order in the source code, this is the formula right here for how many different unique permutations we could have. And we want to eliminate the number of frivolous ways we can reorder things. Like, if we want a how do I say this? We want to reduce noise in our code. And you might say that, well, all these comments all over the place in my code are noise. But what I mean is, there's a difference between having more than one way to do something and then having 50 apparent ways to do something, but those 50 ways are actually only 5 different ways to do something, but they all kind of, but there's these different methodologies are all the same methodology, but superficially they kind of look like they're different things. We don't want any of that in our code. We want to eliminate possibilities as much as possible. We want to the more possibilities you have, the harder the code will be to follow, if that makes sense. So we want our code to be very predictable and very organized, and just we want to be very OCD with how we're organizing our code, if that makes sense. So with this, permutation formulas. For example, okay, so I thought pick was for permutations. So pick is permutations and choose is combinations. So for example, let's say you have 16 people to pick from a 3-person committee. To pick for a 3-person, 16 people to pick from for a 3-person committee. So it's like 3 pick from, maybe, let's try that. So 3 pick from 16. Can we, so there must be a way to, like, there must be a way. It's weird that 3 pick 16 doesn't work, but if we do, like, 4, like, 5, choose 2, whatever, that works. But, like, when I do pick, it, like, the thing that's annoying me is the thing that is annoying the hell out of me is that when I say choose, the Google search kind of is working for me, but then when I use pick, it's like, oh, you mean lottery stuff? No, I don't. So 5 NPR. Let me try that. So, so it looks like NPR. So it looks like NPR is used for permutation. So let's just kind of like take that. And then let's look at our history because we just had the damn thing open. God, the history is so annoying here. It shows my Google searches, but it doesn't show the actual page I was on. So it's like, so let me open up Chrome again, or Torch. So it's just very weird that it kind of looks like with the history, looks like with my history it like if I go to www.google.com and I go to if I do like a Google search, www.google.com, and I Google, I don't know, I'm gonna say, let's say over here I Google something like cats, right? And then I hit this cat, and icatcare.org, right? Okay, so okay, so we're at nytimes.com. So we're at nytimes.com. Oh, it opened up a new tab, so that doesn't really count. But okay, it just seems that my history isn't showing the yeah, so at 11:56 a.m. it just shows the nytimes.com, but it doesn't show. I thought I was somewhere else before that. So if I go back, no, I don't know. So how to phrase combination and permutation calculator. Oh wait. So it's just annoying because I had the answer and then I just kind of like combinations calculator NCR. So okay, so that we have that, we know that like it's like 5 and then n number, choose, and then I don't know what R is. R is R subset of n or sample set. N, the n is the set or population. Okay, so 5 is the set of n, and then R is the subset. And this is 5, choose 3. Okay. Now if we go to Google here for a second, and I know I'm kind of going off the rails here. So if we do 4 NPR3, now, so if we do it like that, it doesn't work. The thing that's annoying me is that 5 choose 2 is working, but 5 pick 2 doesn't give me answers. If I do it equal. So I don't understand why pick doesn't work in Google search, but choose does. Like, why is it combinations are Googleable, but, you know, permutations aren't? I don't know why that is, but you get the idea. So the idea is that there's a lot of different permutations for, you know, how we could organize this code, and we don't want like this artificial explosion of ways that things could be ordered. We want to eliminate as much variability that doesn't matter. Does that make sense? So if the variability in the code doesn't matter, we want to remove it from the code. So one way to remove the variability is the strict ordering of functions. Without any forward declaration, there is a strict ordering constraint on the functions, where if a function calls another function, then that function must appear below the function it calls, right? So since this is the main function that calls all other functions, this function must be below all of the other functions. And with that strict ordering constraint, it makes it really easy to like look through your code and know where to find things. Like when I look at this function, and this function, I know immediately, without having to think about it, that all those functions are above this function, right? Because that's just the way things have to be ordered. Now, a way to make this even stricter than it has to be is, well, okay, we have this 1, 2, and 3. what should the order of these be? Because these don't really need to be ordered, right? They can effectively be in any order they want to be. But another way to strictly order these would be, let's say maybe this one should be the first one above, and this should be the second one above, and this should be the third one above. Should it be like that? Or should it be in the opposite order? Should this be the first one we can find when we scroll up, or should this be the next one we find when we scroll up? Like, how should that work? And why are we going to do it that way? Do we have any reasoning for it, or is it just something arbitrary we have to stick to? So my thought is, as we start going down here to these functions, there's potentially more information in the function body that one of these functions could use. And because of that, this function, depending on how we're refactoring, this function could eventually start requiring this function here and this function here, right? Like when we are, let's say we're doing things where like we're extracting code and putting it into another function, how does that affect the ordering of these functions? So it's just a guess, but I think that well, okay, the more basic things need to be higher up, right? Render scene is pretty high level. Or this function might eventually be able to use the stuff from here and here. Okay, yeah, so that's interesting. So we have to think about the order of these functions, but we also have to remember that there is a data dependency here as well. So the output from this function, right here, is used in this function, correct? So with that, this function kind of indirectly needs to know, this function right here kind of indirectly needs to know about this function here, right? So I think for consistency, because we see this kind of like data dependency here, and same thing with render scene. Render scene kind of like is indirectly depending on this function here, right? Because the data that we get back from here is, right? This variable here and here, right? So there is this strict ordering constraint with these functions, right? It's just not immediately obvious, but there is actually a strict ordering constraint. So the order that these three functions should be within this first degree removed section should actually be the order in which they are called here, right? That would make the most sense. So let's so now that we kind of know that, let's color code these, and we'll do okay, so we're gonna go cyan, orange, and then kind of like an orangish yellow. We'll just call it yellow for the sake of communication. So cyan, orange, and yellow. So cyan, orange, and yellow, that's the order of the functions. That's the order we want to keep. So we could also think yellow, orange, cyan. So this orange thing needs to be in the middle, and cyan needs to be on the top. And so this function right here, this render scene function, that actually needs to be on the bottom right here. Okay, so now that we have render scene on the bottom, we have that correct order. We got yellow, orange, and cyan, and if we look at our token highlighting, we got yellow, and then we have the orange, and then we have the cyan. So we have the correct ordering now. So now that everything is kind of like in a very strict order, what we can do is we can take the hold on, let me clean that up a little bit. We can take this divider that we kind of created, and I don't believe we have another one of these, but we can go Control F and just look for a string of all ones. We can't see it, so we know the other side of the divider isn't there yet, and we can just cap that off right there. So we have our first degree removed functions are now kind of like there. So now the next thing is, well, okay, how do we subdivide the next degree of functions, right? Because we have a problem where it's kind of going to explode out of control if, well, with this ordering, what if these functions call other functions, and these functions call other functions, and these functions call other functions, and they all belong in the second degree removed section, but what is the relative order of all of those? And we want to keep a kind of like that still strict data dependency kind of order between those functions. So let's see what we can do. So let's, first of all, let's just search for any more functions that are being called, and we'll give them some token highlighting, and from there we can, we'll be able to figure out what needs to be organized where. So within here, it almost looks like the only thing that is called is kind of like these utility functions. So we have this error pixel function, which is going to be used to notify us of problems. We got the integer 32 modulus. And what else do we have? We have this struct, but we already decided structs come before all of the functions because it's kind of like functions before functions. Functions are always after data, so data first and then functions, because functions call data, not the other way around. So the dependency order of data and functions is the data always should come first. So we're not going to worry about data. Data just always comes before functions. We're just looking at the relative ordering of functions within all of this. So it looks like the only thing is this integer modulus, and then this first voxel query. Like, where the hell is that being called from? Like, it's not. Did I miss something? And I did miss something. So it is. Okay, so we have that. And so we know in this next section, the most important thing, I32 modulus is a utility function, which means that it could definitely be, it could end up, it is like the most degree removed because it's like this utility that's called by everything else. So it doesn't really make sense to give it a numbering section, but like it could be anywhere, honestly. It doesn't. So if a function is called in multiple places, then the degree that function gets is whatever the highest degree removed from main it could be, right? So if the function is called in main, but then it's also called in a 6th degree removed function, then it's not going to have 1 for 1 degree removed. It's going to have 7 for 7 degrees removed. So first voxel query needed, interpolation 3D. So interpolation 3D is kind of it's a utility function, but we see that it is only called in one place, right? It's only called right here in this function. And so that makes, it makes the interpolation 3D, that kind of makes it a 2nd degree function. So we got that, and then we got that, and then we got I32 modulus, and then we have this pixel error function. So I32 modulus, is that being called anywhere else? Because it is a utility function, but if it's only being called in one place, or in one function, then we can give it a stricter ordering constraint. Yeah, so I32 mod and is only being called in one place. We can kind of like remove that later if that changes and move it into a different degree. But right now we have this get distance, I32 mod, pixel error. We're definitely going to keep pixel error at the top because I know absolutely I'm going to call that in other places. But as far as some of these utility functions, I'm going to keep them as strictly ordered as possible. So with that, let's take SFD I3D and the get distance and voxel, or dis and vox. Is that what the actual thing is called? Yeah, distance and voxel. Why is it called dis and vox? Hold on. So that's a name, alright. But, does it make sense? And dis and vox doesn't make sense here. So we have voxel current, and we have, voxel distance. So this really should be named, cur and distance, yeah? We could also call it like, so vox cur and vox distance, right? So what I kind of think here is that, so I'm uncertain of the name of this. Like, I don't know. I feel like it could change eventually, and I'm not certain of. This name is obviously not normalized because we have distance here and then we have voxel here, right? And you see that voxel is this first more general category, while distance is a subcategory here. So this name is very inconsistent. The name actually is this name is actually trying to say what members we have in here. So we're kind of naming everything based on what the actual data is. Kind of like a Lego naming convention where we're just kind of like, we're doing some agglutinative naming to the extreme, where we're not even going to give this name like the name of like, we're not going to give it some fancy name like voxel info or something. We're actually just going to name it based on what the actual things inside of it are, which could spiral out of control, right? Because what happens when this becomes a subcontainer of something else and something else, right? So that could definitely spiral out of control. But the idea is that we want to have like a really good hold on what the actual data is and the flow of information, right? So we don't. That's the most important thing. So as far as thinking about what this should be named, I think this should be named. We have current. We could name it Vox because we have Vox cur and Vox distance. We could name it that, or we could call it cur and distance, right? I think we should just call it Vox because I think that will, or we could call it Vox cur dis. I don't know. I don't know what to call it here. Or we could call it voxel VCD for voxel current and distance. And that would keep everything kind of shorter, which would be nice. Though I do like this naming here, right? RWC and RWN, and then you see RWC and RWN. So there's no, with this name here, it doesn't add extra cognitive load because when we look at this, we instantly know RWC and RWN. Okay, so there's an RWC in here and there's an RWN. We don't have to think about what this struct actually means. We just know it's a container for these two pieces of data. We don't have to come up with some type of new word for this, for just putting these together, right? We don't need to actually think about that and invent some new word, which it takes time to invent the word, and then it takes time to remember the word and be like, what was that new word I created? Like, I don't really want to do that right now. I have done that in the past because it is nice to have make up a word that is, instead of using a Lego name, come up with like a fanciful name and have that word have a very specific definition. So you could have a struct name like like we could call it, I don't know, Bobcat, right? And Bobcat always means this and this. It doesn't mean anything else. It always means exactly that. And having that kind of explicit definition that has an exact definition can really help us here. But this has less cognitive load. So we're gonna go with a kind of like a stripped down. We want the code just to be as easy to follow as possible, and we don't really want it to be human readable. We want the comments to be more human readable, and then we just want the code just to be we want it to be readable, but from a logical standpoint, a symbolic standpoint, a logical standpoint, but not like a we don't care if it sounds like English, right? We don't care if the code sounds like English, but we just need it to be easy to reason about, if that makes sense. Okay, so with that, I said I'd like this because the subcomponents in there make sense. So with this voxel current and so here's what we're gonna do. We're gonna go vox cur. Okay, so we're gonna rename these structs. So we're just gonna call this. So we're gonna combine some of the methodology here of having like a terse name that has exactly one definition, and we're gonna call this voc for our voxel current. And then over here, vox dist, we'll call this vod. So distance information, and then eventually you might have like another one called like vom for voxel material. But right now, we're just going to be as terse as possible. And then over here, right, we'll just rename this to voxel current. And then dis and vox will be renamed to dis and vox will be renamed to voc and vod. But first, let's make sure we're not screwing anything up, because we're kind of like refactoring, and let's see what we've already broken by changing that. So let's run that. Okay, so that still works, because if we look at where dis and vox is called, we're probably like using them all directly and not like breaking them out of the container. Yeah. So this really is, right here is really a top-level voxel container, voxel information. And so what I'm thinking is this really shouldn't be called voc and vod. First of all, voc and vod is kind of like a weird name. But if we look at current and distance, Um, so we're going to take distance and voxel, and we're just going to call it uh, the thing is with calling it just Vox, the problem is that we have potentially just a lot of problems with that name being, if the name is too terse, then it can be very hard to find the struct definition anymore because we have something called Vox like all over the place. So what we could do is we could call dis and Vox. We could just call it Vox 000, and that will be like the main voxel information container. And then with current and distance, we can still do the name stuttering of if this is called Vox 000, and this is called Vox cur, and this is called Vox dist. And the reason we have that name stuttering is because if we just call the variables cur and distance, well, there's going to be definitely more than one current variable, and there's going to be more than one distance variable in our code, like absolutely, and they could have totally different meanings. So we want to make sure that if we kind of like double click on a variable and try to look for where it's used, we want to make sure that it has the exact same meaning everywhere else in the code. So we want this good balance between, we want the code terse, but we don't want it so terse that we can't find anything because you're using the same name for different things, right? We want it terse, but we also want it unique, unique in meaning. So, voxel current info, voxel distance info. Okay, so that's kind of like the parts, and so we'll take this and we'll rename this as Vox 123 Vox 000, and we gotta make sure that we match the case here because we're also gonna find places where we're using the lowercase, right? So uppercase, all uppercase is going to be used for the struct because a struct is much like a define or a constants where it can't change, right? The definition can't be reassigned in your code, right? So since this can't be reassigned, we can just name it all capitals as a convention for our structs. And then with our functions, I usually like to use camel case, but then I also like to keep the transformation apparent in the function. So if there's a function that gets vox cur, it'd be get underscore vox cur, and then there's absolutely no camel case in the function anymore because I wanted to keep that exact name so I could easily find it. Okay, so let's look for the same thing, but we're going to look for the lowercase TLCMD. Okay. So now when we look for lowercase, we can see it right here. So we're going to take so here's an example of one of my functions where there's absolutely no camel case in it because this is the variable name we want to get, and we want to use this data here to get that, right? So I'm just being as transparent as possible with the data flow, where you can actually see the data flow within the source code. We don't have to like run a debugger or use any special IDEs. We can kind of see the data flow of the function just because we use some very clear naming, right? And the naming isn't clear in the sense that, like, oh, it's very human readable. It's very clear in the sense that everything is very normalized and terse. So we ran that, and that still runs, so that's good. Okay, so now that we've kind of like renamed that, so we got like our first degree removed functions, and then our second degree. We were in the second degree, we kind of like refactored some stuff. But now that we are, let's get back to actually finding the second degree functions. So we have the I3D. There's another function in here. So in the ray march loop, we had another function we were calling. So it's this one right here. And I32 mod. So we have these three. So what is the order that we're going to put in the second degree? And so for the second degree section, so everything is going to, we don't want to think too hard about this. So, right, this is nested into here, and this is nested into here, and this is nested into here. So eventually we get this very large branching structure where different functions are nested into other functions that are nested into other functions. And so the pressing question is, how do you take all of that branching, all of that that branching structure, which is a multi-dimensional structure, how do you take that multi-dimensional branching structure and linearize it in a very deterministic way? And so the way we're going to linearize this is we're going to look at everything in our first degree removed functions, and we're going to put it into the second degree removed functions by the order that it occurs when we're just linearly scanning through here, right? And that'll keep the correct data dependencies between everything. So we see SFD I3D, the get vox function, and then the I32 mod, right? That's the order they're called in, so that's the order we're going to shove them into the second degree. So we're going to color code this again. So we're going to do cyan, and then we have the voxel function, cyan, orange, and we're going to ignore the pixel error because I just know that that is going to be called by everything else. So I'm not going to worry about that just yet. So we're going to take that cyan, orange, and yellow. So we've got to look for the functions above that are cyan, orange, and yellow. So here is our yellow. So we're going to take this yellow section and we're going to put it in here. And since color that back to yellow. And this is orange, okay. So we got cyan, we got the orange. And then yellow. So this is the yellow, right? No, this is the cyan. Cyan, orange, and yellow, right? Yeah, it's already cyan, so of course it's cyan, right? Okay, so we got cyan, we got orange, and we got yellow. So we got those in the correct order, and when we look at down here, we can see the cyan, we see the orange, and we see the yellow. So that is the correct ordering for those functions. Okay, so now that we have this strict ordering and we have these second degree functions, we can look at, okay, well, what else remains and figure out where to put that. So we have no halt, use error pixel. So that is for our pix error function. So we're going to do this again, where we have a description of the function and then we have the actual function name. So that way we can kind of like quickly go from here to see, you know, the borders, but then if we click this, we can actually see where the function is actually called. And notice that we also used a variable with the same name as the function, and that just makes it easier to see where the data is connected. So we're going to take this, and we'll go down to the bottom of the function, and we'll just put that over there like that. And we know that the air pixel is something we wanted on the top, and oh hey, look, we're already at structs and stuff. So we did a good job to where all of the degrees are kind of like where they belong. So now, really, like I said, this halt function is really an infinite amount of degrees. And I don't know, you could just use I for infinite or not. Let's just keep okay, we'll just make a note of what this I means, you know, infinite degree functions. And then, right, so we're getting rid of so instead of this numbering, right, we're just gonna have these I's, because eventually what we're gonna do is, as we write more code, we're gonna have, instead of a 2 removed section, we're eventually gonna have like a 3 degrees removed or something like that, right? So everything's gonna like change its degree removed eventually. But this kind of like helps us know like what section we're in, right? We know how far away from main we are, right? So if we're at 0, we know that this is the main code, right? If we see these zeros. If we are at 1, we kind of like know we're 1 removed from main. If we're in the 2 section, we know that these functions are 2 removed from main, etc., right? And if we're at I, then we know that we are all the way at the top, that we are we're infinitely removed, or we could say indefinitely removed, or we could just say T for top. I don't know, but we'll just keep I for now. So now this next section up here, right, we've already indented this a little bit. So what is this? And really what this is our data section is what that is. So we could... It's kind of weird that we're reordering everything in the orders here. The ordering here is kind of like a top-level thing, but you really would say that, well, if we're gonna take this indentation here and we're gonna call this the data section, shouldn't we like indent like all the functions and call that a function section? And that would be like a normalized way to do things. But the problem is that there's so many ordering constraints with all of those functions that you end up getting this like one gigantic area of indentation for where the function section ends and begins, that indentation is no longer meaningful, right? Like this indentation here, which is mostly blank space, right? We want it to all of a sudden like have a few characters eventually, otherwise it's meaningless, right? Like if we there has to be some type of characters that split up that indentation level, otherwise it doesn't really serve a purpose anymore. So with that said, let's take this and we'll just call this we'll just use D for data. And then we'll just say D data section. Okay. And right. You know, how we want to organize that, I don't know. Well, yeah, so since this is kind of like getting out of control here, we just want a way to where we can split up everything and have kind of a line hierarchy. So I went to art school, so when I'm writing the code, I am looking at it from like what are the artistic merits of some of this code. So okay, so this is M macros section. Okay. And what is... Okay. And then, so U is, so there's a very specific reason for what this section is down here, right? This is undefining macros. Now, really, we don't need this section in our GLSL code because it's like this one piece of code that is, it's compiled without any reference. It's not like connected to any other source code, right? It's not, this code is not part of a larger project. Well, it is, but not in the sense that, like, this is, when we compile this is all there is when we compile it. There's no other code files. And since there's no other code files, we don't have to worry about these defines leaking into other code files. So we really don't have to undefine these, but for a good, consistent practice, I do want to undefine these macros, just so that, you know, I have a way to, what do I want to say here? I don't even know what I want to say here. It's just good to be as consistent as possible. So even though it's not necessary for the GLSL code, this is what I do in the C code that I write. So we're just going to keep that consistency here. Now let's look at this documentation section. We have this extra layer of indentation here, which isn't really used. So what we could do is... well, the thing is, we already have a string of Ds for data. So what I'm thinking is, this extra layer here, let's remove that extra layer of indentation really quick. And let's expand that. So we have this documentation section, and how are we going to reorganize the indentation here? Like, we don't want to waste any indentation, but we want the indentation to always be kind of like meaningful. So, we have this extra level of indentation we could possibly use, or we could, what do we want to do with it? So, or do we want to just be like, oh, that's great, we have some extra room, right? Like, how do we want to think about this? So my thought right away is, well, with these extracted block comments, we have this indentation level here, and then we never indented here because we were running out of space. So we could take advantage of that, right? And just indent like that. And I kind of like that. And then original comment and all this, right? We can indent that. And that's helpful, right? And then we can expand the indentation here. And I think that is, I think I like that. So extracted block comments, and then with functions, what we can do is we can take this and we can indent like that. And then with identifiers, we could also make this as capital. So identifiers. So identifiers, indent like that. With abbreviations, right? We can take abbreviations and then we can also indent, right? So now we have kind of a, we've used that extra layer of indentation, and we've made it kind of meaningful, right? So the first level of indentation, we've indented for anything that is inside this documentation section. and then the first subcategories, right? So subcategories of documentation, abbreviation, identifiers, functions, and extracted block comments, we have indentation for that. And then for all of the sub stuff, we have indentation, right? So that indentation just makes it nice and easy to visually parse. So this looks pretty cleaned up to me. Now the problem is that as we go about, things are going to change. And things will change, right? So for this, we'll just have this star kind of header for the top. So for the so we have this extra layer of indentation that we've kind of lost, and for that, I'm just gonna back that out there and allow for us to have just a little bit more room to write stuff. And that looks kind of good to me. The other thing is we might want to be a little bit decorative, right? And we might want to think about how we can utilize some of that extra padding we got and just make it kind of like noticeable. So okay, so I like that. So we got this nice little block for the kind of the information for how to like find everything, and this actually has none or to do. This is a to do, and this is also a to do, right? Because this is our next iteration of the same file, and I'm getting to the point where I really just want to write everything over from scratch, but it took a really long time to get here, and we never got anything substantial written. Like we got a good like little framework written, but not enough to where we didn't get enough written to in the time duration where I'm like, it's time to scrap it and start over. I think we need to just take what we have and kind of move it over to another file and kind of like append to it and add to it. So now that we have this, I'm going to take 8, so SDF 8, I'm going to remove that. SDF 7 I might still want to keep for reference because I think that we still have some valuable things in this attempt we tried. But it looks like it's... Well, let's look at it for a second. Yeah, we have like all this trash right here. Like we have all these different cases for like trying to debug stuff, and that really cluttered stuff in this version. So that's why we took the time to make a pixel error function to kind of standardize how we're debugging, so that we don't get a whole bunch of cruft or noise. We don't want this much noise. Like, it is good to be very paranoid, and yes, we might want this type of functionality where we're paranoid and we can kind of see when things go wrong, but having this much visual noise in our code where it's all debugging, there's no logic here, that can be kind of bad. So we're going to try to avoid that if we can. So okay, so we have this, and we've kind of refactored it. We've made everything nice, and as we start adding code to it, it's going to get messed up again. But we're not going to worry too much about how things get messed up. So as we need new functions, if we add a new function to this code, we will always add the new function directly above. We'll always add the new function kind of like directly above wherever it's being called. That way it has a correct compilation order. And then what we'll do is we'll surround it with, I don't know, maybe we'll use stars or something, right? We'll surround it with some type of pattern where we know that it needs to be moved, right? We'll have a way to refactor it. Okay, so this is working. Now I need to figure out where this magenta color is coming from in the background. And we're going to have to get our bearings and be like, well, where do we set magenta? Where is that? Because right now I have no clue in this code, right? There's all this code, and it's like, where the hell could magenta be coming from? So the first thing is it's definitely coming out of SDF render scene, because this is the only place frag color is being assigned. So if we look at SDF render scene, we see a whole bunch of code, and we see this color 4D, right? And I know color 4D is the output color here. So something in color, so one of these color 4D assignments is where that color is being assigned. So if we look at this table of colors, we see different colors, and we're like wondering why is it? Okay, so we have this slice render. So I remember that slice render is for if we want to render orthographic cross sections by using the camera plane to just slice through geometry. So I'm guessing that it is somewhere assigned here, and I honestly think it's probably inside this to-do, because we're wondering why is it not rendering as a checker? Like, we're supposed to try to get this checkering pattern, and we don't have one, and why is that the case? So when we render like that, we see, okay, we're getting rid of the purple. So something about this is not getting us any purple color, and it's like, why not? Because we have this camera plane, and what's going on there, right? So now that we know kind of like where we're at, we can try to figure out what's going on, right? So we have this table, this color table, and table is kind of like an ambiguous thing here, where I know that we have different tables. So yeah, we have this other table, TAB, and you know what I said about we want to be terse, but we don't want it to be, we don't want it to be, let's get rid of that, because that's really annoying to like control F through it and get all that. So if we look at this table is completely different. It's kind of the same functionality, right? It's a table of colors, but it's used in a completely different spot. So we want to have a more refined name, a less terse name than just TAB for table. And usually when I take variable names and I make them less terse, I always organize things from general to specific, right? So we have these two tables. One is a table for errors, and the other one is table for some type of checker colors. So so what we're going to do is we're going to take this table, and we're just going to call it table of error colors, or tab error. So it's table error, right? And you'll notice that when I do this, I'm not reading it like English, right? Table errors, it would make more sense to call it error table, right? We got that like what is it in English? It's like a subject verb. I don't know how it goes, right? But in English, you usually have this specific constraint of like how you're supposed to order things for it to sound like natural English. We're not worrying about it sounding like natural English. We are worrying about it having very strict ordering constraints. So the ordering constraint of general to specific matters more to me than the code sounding like English. So we'll take that and rerun that. That's good. And so now we'll look for other places where we have TAB for table. And here's the other table we have. And this is checker colors. So so it's a checkerboard. So we could call it C. So usually when I use CHK, I use that for like checking values, for like debugging, for like assert statements. So I don't really like using CHK for that, because that means table of check values. So table of so when you really can't think of a name, one way you can do it is you can just call it, it's table 0, right? Table 0, done, right? Forget about trying to name it something meaningful. Just call it table 0, and table 0 is different than table error, right? And that can help us identify it, right? And table 0 will always be this checker table, right? So given that, let's take the code and let's paste it. Let's make sure that still runs. Okay, that still runs. So now that we've looked at this, we got to figure out why is it that when we select from this table, it looks like we're always getting that magenta color. And so first of all, where is the magenta color that we're looking at? So red, green, and blue. So it is something that's selecting colors from here and here, but there's nothing in the middle. So it's not this, and these are, if the colors are right next to each other, then well, it's not magenta, right? So these aren't magenta, but these are magentas, right? Yeah. So out of bounds is magenta. So I wanted out of bounds to be a color that doesn't quite indicate an error, but doesn't indicate a good thing either. So I kind of used magenta for that. Originally I wanted like a gray, but I want this to kind of be distinct from the error pixels, and all my error pixels are gray right now. So we're gonna stick with this, and I'm gonna say magenta for out of bounds. And then for this, it is this is red and yellow, and then we have red, green, blue. We have blue and cyan. So this was originally supposed to be different layers of gray monochrome, so that's why we have kind of like the darker magentas for the first layer of checkers, and then for the second layer of checkers we have this. So really what this is like layer 1, this is layer 2, and this is right here is checker 1, and this is checker 2, right? That's kind of like what we have going here. So let's reorganize that. Just want to organize it in a way where we kind of like lay 1, lay 2, right? So, and let's make sure that our logic makes sense up in our picking logic right here. Let's make sure that logic makes sense. So, if we are actually inside the voxel volume, then we multiply by 4, right? So we take 4 times 1 or 0, right? So if it's 4 times 0, we end up at the 0th place here. But if we multiply by 4, we get 0, 1, 2, 3, and 4. So we end up here. So we end up in the inbounds layers, right? And then if the layer is 0 or 1, the layer could be 0 or 1. So if we're at layer 0, we don't add anything. And if we're at the next layer, we add 2. So 0, 1, and 2, right? Okay, so now for the checker, right? So which checker color do we have? We add 1 or 0. So we're here. And if we're at checker 0, so we're at the even color, we're going to be here. And then if it's 1, we're going to add 1, and we're going to be here. So this branching logic makes sense. So basically, this is just a big if-else statement. This is a big if-else statement that we're using math to create our branching logic with, just to keep it as terse as possible. So let's look at where is that... well, first of all, let's make absolutely sure that we know what this magenta color is that we're looking at. So I believe that looks like a darker magenta. And so I think we are on layer 1, but I don't know if we're on... It looks like we're on this one right here. And so to see if we're on that or not, what we can do is we can... F32 x equals 1.0 temp do not temp use only. For okay, so X is going to be used for debugging colors. The reason why I didn't want to say temporary for debugging only is because that would give you the idea that I want this variable removed eventually. I actually want to keep this variable here, but sometimes I'm just not going to use it anywhere. So I'm just going to put that X right there, and we're going to make sure that that is the actual color that we're looking at. So that did not change. So it's not that. So we're going to put an X over here and see if that changes things. So X, put that over there, and see if that changes things. So that doesn't change anything. So I think I'm looking at layer 1, but I'm actually looking at layer 2. And we might want to actually call it layer 0 and layer 1, just so that the math kind of lines up, so that we're not confused about that. And then we can also call this checker 0 and checker 1 as well. Okay. So let's, so we know it's absolutely magenta. So what we're going to do is we're going to put an X there. And this is kind of tedious, I know. So, okay, we found it. So we are on the second layer, but the first checker. So what could that mean? So out of bounds, it makes sense that we're always going to be on one layer or the other, because the camera right now is kind of perpendicular to our layer cross sections, right? So the camera is always in one layer at this moment in time. That's what I expected for that. Now, as far as this checker pattern only being replace with when okay. So this extra comment here, I wanted to maintain that this is the same block, so I thought making a space here kind of like disjoints this a little bit, so I'm going to keep it like that. And I might also want to do something like this, where okay, kind of odd, but the idea is I want to maintain that there's like a block of stuff here. So I kind of just did that just to make it a little bit more noticeable. Okay, so why is there no checker? Because the idea is that that camera should be in different voxel cells. Even if those are out of bounds voxel cells, they should still kind of exist. So with this checker, we know that we get to the layer by taking layer and multiplying it by 2, right? And then checker. So if we look at this, the layer is always in bounds. So we have some good debugging there, where we know we would see a color problem. So this is, we have the error message is just define. We have the original color for the output, and then we have this OK variable that we post increment. So the idea here is that if OK is not equal to 1, or post decrement, sorry, post decrement. If OK is not equal to 1, when this function gets called, then we use the original color. And the reason why we do it this way is so that if this pixel error function is called later down here, we won't see that color. We won't see a reassignment of the color. We'll always see the pixel error that is the first error that is happening, right? Because if an error happens up here, then we're all of a sudden we're in a undefined state. The program is in an undefined state once an error happens. So any error that follows after that is completely meaningless. So we want to always address the first error. So if this is called second, OK will already have been a negative value, and the code logic for this function will say, okay, there was already an error state when this function got called, so we are going to take whatever the color is here, and we're just going to pass it back down here without actually doing anything. Okay, so with that, and also with the error numbers, that's just because I didn't want to write a descriptive name, so I just normalized the error numbers sequentially in the order that I create them. And these error numbers should only be used in exactly one spot, because we want the color of the pixel to be able to accurately identify the source code, right? So we're looking at this screen over here of colors, and we want to be able to figure out, like, where is that error coming from, right? So we have to somehow get from pixel colors to where the hell is that code, right? And that can be very difficult, so we want to be as meticulous as possible, because if we aren't meticulous about this, we are going to we're going to get lost. So let's see what else we can do here to figure out where this problem is coming from. So how is the layer being calculated? So the layer is TZ, and I already know TZ doesn't change, right? So layer, so it's this checker. The checker is the thing that's going wrong, right? Because we're over on this layer, right? We're always going to be on the same layer because the screen plane is perpendicular to our voxel layering. So what we're wondering is, why aren't we switching back between this choice and this choice, right? To create like this checker pattern on the screen. I highly doubt that one voxel is taking up the entire screen, right? That would be one reason why we wouldn't see any checkering. But I know the voxels are like, each one is 16 by 16 pixels in size, and we're using the fragment coordinates, like the pixel sizes, as our native coordinate space, so that doesn't make any sense. But yeah, so why are these checker values wrong? So if we look at here, let's just make a note here. CHK0 or CHK1, and then this layer here is going to pick between lay 0 or lay 1, right? So we just know what that is doing. Okay, so let's see where checker is being assigned here. So we got this crazy modulus logic here. So I'm instantly thinking, you know what? My modulus logic is probably wrong, right? So we got tx, we got ty, and my thought was, okay, this is going to create a checker pattern, and then this creates a checker pattern, and that we want to stagger the checker pattern. So this is a checker pattern on the x, a checker pattern on the y. So really this is a stripe pattern, and this is a stripe pattern, and we want somehow to interfuse these two striping intervals on the x and y to create a checker pattern. And we went wrong with the math, and let's take this for a second. Let's take this logic right here, and let's try to analyze it by writing a diagram. So rather than trying to, sometimes I will write some JavaScript code to try to debug things, but that's extra code we have to write and maintain. So I don't want to do that, and I don't want to. That's hard. It's more work. So what we could do is we could think about these two data sets. So we'll call this set 1, and we'll call this set 2, and then we'll call this, and this right here is set 3, right? So for our OCD-ness, we'll do 1, 2, and 3 like that. So we got set 2, set 1. Well, then that's an X. We might as well move that around, shouldn't we? So let's take that, and let's. So I just like the X to come before the Y, and that's kind of why I'm reordering this. Okay, so now that we have that, we'll do set 1, 2, and 3, right? So we got the sequentially ordering here so we can reference what these different things mean. And so we know that set 1 is going to be like something like, it's going to be like a 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, right? That's what we're going to get for set 1, right? And then for the set, for set 2, right, we're also starting at the origin, which is 0, 0. So we're going to, so this is our set information for the other set, right? So if we have these two sets, if we modulo those together, so we take this mod that, so I already see a problem here, right? That's never going to work, right? This mod that, well, the remainder is 0. This mod that, the remainder is 0. So that's why we're always getting 1 for the output, right? So this equation right here, that always leads to 1. So we have to figure out how we're going to fix that. So what we could do is, you see how we're doing mod 2 here. Should this all be should we add 1 to that, right? Should we add 1 to one of these sets? So what we're going to do is, if we add a 1, 0 mod 1, so 0 divided by 1 is, that's still going to be, so let's take a look here at the sets, but let's look at this in actual, set 1 is like a 0, 1, 0, 1, 0, 1, 0, 1, right? Like that, all right? And then the set 2 is kind of like, I don't even know how we'll write it, but let's try like that, right? So set 2 is like this. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, and 7, right? Okay, so these are our sets of data, and so I've just taken these sets, and let's make sure that our sets are exactly the same length. So let's take that, and so we just kind of move this into two-dimensional space so that we can kind of reason about it a little bit better. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. Okay, so now that we have it like this, we can try to reason about it, where if we mod these together, 0 mod 0, that's going to be, and let's give that a little bit of space, like that. Okay, so okay, so modding these together, 0 and 1, so and actually this is this mod that, so it's well, hold on, x and y, that's x and y, right? So this is x and this is y, right? Because this is like a y-axis. And our y-axis is, man, I keep on screwing this up. So we should have x and then y like that. But then if we have that, then Okay, let's not worry too much about the naming here. So we have the Y set, which is set 2. We have the X set, which is this set, right? Um, uh, okay, so we're always going to take the first set mod the second set. So 1 mod 0. Well, 1 divided by 0 has a remainder of... well, actually, divided by 0 is just bad fucking news, right? So we already know we have a problem here. So what I would like to do is... we already know that this is wrong, right? We already know that... we don't want to mod by 0, right? Because mod is just the remainder of a division, and so mod 0 is actually a divide by 0. So with that said, we're going to take this and we're going to do plus 1, right? And that kind of makes sense for staggering, right? And then for set 1, or, we're not going to call it set 1, because, this ordering constraint is getting kind of confusing, so we're just going to call it set y and set xxx, and we'll call this set 3. We can keep set 3 like that, but I just am continually getting confused by that numbering. So, so set x and set y. Okay, so now that we have these sets here, we can reason about them a little bit better. So we know that with set x, because we're taking the y and dividing by x, doesn't really matter how we do this, like which one offsets the other one. It just matters that we have some type of offset. Because usually I think I would do this the opposite way around, but let's just try to get this working logically, and let's not worry about which one's x or y. It really doesn't matter, as long as one of them... yeah, let's not worry about that. So let's just do 1, 2, 1, 2, 1, 2, 1. So, right, so we're going to take... so before it is, right, so we take that and then so this set right here is basically this, but we offset everything by 1. I mean, that's not the best notation, but you get the idea, right? And then we got 1, 2, 1, 2, 1, 2, 1, right? And so now that we have that, we can go 0 modulus 1. That's still 0. 0 modulus 2. So anything with 0. So the problem is that anything with 0 here is going to be it's all going to be yeah. So okay, so we see the problem that if it's 0, it's always going to be 0, right? No matter what we modulus it with. So the offset really shouldn't be like that. In fact, we should take these two sets and they need to be added together, and once we add them together, then we can modulus them by 2, and I think maybe that'll give us the right answer. So, so let's take those sets, and if we add them together, so we don't need to just add them together, right? Because if we add them together, we get 0. We're going to get like a 0, 2, 0, 2, 0, 2, 0, 2. But let's just add them together really quick. Like that. So we have... Or actually we don't. We get 0, 1. But then over here, we add these together. We get a 1, 2, 1, 2, 1, 2, 1, 2, like that, right? And then over here, this is a 0. So we get a 0, we get a 1, we get a 0, we get a 1, we get a 0, we get a 1, we get a 0. Okay, so now we have something we can kind of work with where if we mod mod 2 this and mod 2 this, we get 1 and 0. If we mod 2 this, are we going to get a 0? Yeah, we're going to get a 0 because it's even, right? So is the even oddness of this creating a checkerboard, right? Even odd, odd even. So our odds are our kitty corner and our evens are kitty corner. So this is the pattern that we need to be creating when we're trying to like do this modulus math to create a checkerboard pattern. Okay, so now that we kind of like know how those sets are going to combine, we know that, yeah, we just got to add those together, and then we just got to modulus by 2. So just put a comma there, and we'll put a 2, right? And we can see that we can see that that's odd and even, right? Now this is kind of a big comment. So we'll take this and we'll just say combine sets so that they create a checkerboard of odd even values, and then convert even to 0 and odd to 1. So that's the logic we got. That's the logic we actually need. So now that we know what the correct logic is, we can go over to our actual code, and we can just paste that in there. And we can't, so this is obviously like a big chunk of code here. So what we're going to do is we're going to take this code here, and we're going to just make a comment, and we're going to say comment modulo checker pattern, right? So we make that comment there, and using that, we can reference that diagram we created down in here, right? So we have these different extracted block comments that we created earlier, and we're just going to paste all that stuff there. And so we no longer need this stuff here, but we no longer need these comment characters now that we're kind of inside this block. But it could be nice to just have that. So we'll name this modulo checker pattern. And actually, we're going to use just 1. And then over here, we'll close that off. So now the indentation for this is indented a little bit, like 1 more than it needs to be. So let's put it back like that. And you know what? I'm fine with that, even though it's kind of... I'm gonna... So I have a commenting style where I put semicolons after the comment so that I can see... so that it color codes it for me, but I'm going to remove that color coding so that this whole comment section kind of has this uniform coloring, and when I see the blue, I want that blue to let me know that there's a section divider, right? So thinking in the terms of the fast and slow thinking related to how your brain works, we want to be able to very quickly parse the visual data by having these stringent ways that we're organizing the shapes and colors of things. So that looks good to me, just putting this big chunk of stuff offboarding it somewhere, because really when we are looking at the code here, we do not need to see all of that, right? Like once you understand how this works, we don't need to see it again, right? It's like, okay, if somebody hasn't seen it before, right, then they can go to here, they can see the hashtag, whatever, and then they can go to the comments section really quick and go, okay, what is that all about? And then they can, read the diagram, and then they can just pop back to where they were coding. So with that, let's take all that and hope we didn't make any syntax errors, and hope we get a checker pattern, because okay, cool. So we have a checker pattern. Awesome. So you know, so we didn't have to use a debugger or anything. We just had to like meticulously diagram it out. And the reason why I chose to meticulously diagram it out to solve the problem was because now it's not just some wasted time debugging. This time that we took to debug and find the solution also resulted in this asset of a nice little diagram that we can now put in the comments. So that's a huge plus as far as I'm concerned. So now that we have that checker pattern, we know that we have this X that we put in there to debug, and we can get rid of that X, which would make it I guess it made it kind of a greenish color because it was the highest intensity channel. So let's take all this and let's just paste it back in there and make sure that we kind of see this magenta cross section. Okay, so we kind of see this magenta cross section, and originally when I did this, I wanted the checkering to be very similar shades so that we can identify this section of checkers as some type of cohesive unit, right? Because we have the different checkering layers, and then we have like the out of bounds checkers, and we want some way to visually distinguish them by grouping the colors in a logical way. And when I was first doing this, I thought that the solid color I was seeing was because I didn't have a different enough color value, and so I separated those colors by more than they needed to be separated. So when we're looking for the white-gray, I'm guessing we can separate these by just one by 10%. Yeah, I bet we can separate these two values by 10% and these values by 10%, and we should be okay. So we're going to go separate these, because I believe the dark gray is what we're looking at, the dark gray shading. But I'm using gray in terms of intensity. Is that not what we're looking at? Okay, so that's kind of... We just changed it and we still have the same checker pattern. Hold on. Hold up there. I thought we just... Oh, was it this one we changed? Maybe I'm not paying attention. So let's put that up there. So we have kind of these extremes. These extreme monochrome. Okay, yeah. So we got this monochrome gradient, and then we have separated by 10%, and then this monochrome gradient's also separated by 10%. So we have a, I said gradient, I meant checkers, right? So we have dark monochrome checkers, and then we have light monochrome checkers. We have these different eyes for intensities. So it looks like for the colored regions, we just used a different strategy for that. So I'm not really sure I want to do it like... I kind of see why we might want that distinction between those layers. So let's do that. So we have... Right now we're using dark to light, and this is the darker one, and this is the lighter one. Darker, lighter, darker, lighter. Okay, so we should really have the capital letters as lighter, because when we think of a capital, we think of a capital as shouting, right? As something more extreme, not less extreme. So we really should have the intensity of of this color should kind of like be less than the intensity of the color that's shouting at us, if that makes sense. So we'll use full intensity here, and then we'll use kind of like this low intensity, or we could use kind of like a and I kind of screwed that up, didn't I? Low intensity, high intensity, and then and the way we separate these two different color layers is we have there's different ways we can group this. So we'll say that the valid layer, yeah, we have a lot of distinctions here between these different layers. I don't know if we really need that much distinctions, but we want some type of way to have like a very distinct checker pattern and just be able to kind of see what's going on easily, right? To be able to visually debug. So let's stop being so picky about how we're doing that, and just make sure everything still works. So okay, that works. So the next thing is, how are we going to get some type of feedback here? Like, do we really have a cross section, or is there, or are we really looking at a three-dimensional cross section right now? That's what I want to know. So the way we could really quickly find out if we have a three-dimensional cross section is we could go to where we're creating that screen rectangle, that like polygon in three-dimensional space that represents the surface of the screen, the thing we're kind of like mapping onto, and we could toy with it a bit, right? We could hack it up a bit. So, like, cool thing with this little diagram is I immediately found the code I was looking for because I just found that diagram, right? I didn't have to read any of the code. I just see that diagram and I know I'm in the correct spot. So with this polygon here that we're creating with vertices A, B, C, and D, so quick thought here. I know I use this A underscore B underscore thing just so that this kind of is consistent. But now I'm noticing when I highlight these, I don't really see it in the diagram because there's no like underscores around that. Actually, we could just change that in the diagram if we wanted to. We just do A. I think that's better just because B, A, B, C, and D, they're very generic letters. That kind of makes things that makes the diagram a little bit harder to understand, right? It doesn't look, that breaks the visual quality of the diagram. So you know what, I'm gonna not do that. You're just gonna have to be smart enough to know that A, B, C, and D corresponds to this A, B, C, and D. I think if you're programming, you're smart enough to understand that, right? And these A, B, C, Ds are the actual variable names, so that'll kind of help make that connection. So we'll keep it like that. And let's look at these. So the Z value for all of these is the same. And so that means that this plane is just going through it's perpendicular to the XY plane, right? So that's kind of why we only have one layer of voxel coloring, because we're not going through any other geometry. So what we're going to do now is we're going to hope that if we try to like, if we take this A and we just sink it down to something, or we make it negative, right? If we do that, we should see some type of different pattern where we see some weird, funky cross-section kind of stuff going on. So let's take that, and we don't at all. Okay, so, well, what is H? H is 0 minus 9. Okay, so that's not good. That's that tells me that the math for, well, no. The voxels are 16 by 16. So let's put a breakpoint here. Make sure it's our only. Let's remove the other breakpoints. The voxels, if we look at how big our voxels are, we can see that the number of pixels in a tile is 16. So our voxel size. So we can make a note of size of a voxel tile measured in pixels, right? So that's what this is, right? So we're thinking of everything as just a tile map analogy and just extending a third axis to that. So the number of pixels on each axis is just 16. So now that we know that, if we go back to here, well, the camera plane, the height of the camera, is at h, which is 0 minus 9. So that means that if we just go 0, we haven't spanned a range of values that is greater than 16, meaning that the camera could have been skewed, but it wouldn't have changed which voxel we were inside of. And we have to remember that the camera is orthographic, so we're orthographically looking down on it, and we kind of like took a cross section that kind of tilts down, but there's no perspective here, so that's why we would not see any distortion. Even though there might be some distortion, it's orthographic, so we don't see that distortion that's happening, because we got to cut through some other layers before we start to see that. So what we're going to do is we're going to use we're going to call it BUG for bug. And we're going to call it we will put it, I don't know where we'll put it, float, and actually F32 is what we do. We've been using F32 for float, so let's change that right now. And F32 bug, and DBG. We could use DBG for debug. DBG equals so it really doesn't matter what direction we go in, but we could do like we could do well, since we are kind of slicing through the Z, we could do number NPZ, the number of pixels on the Z, and then times 4, so we can slice through kind of 4 layers, right? And 4.0 debug only. Sure, whatever. Let's not worry too much about that variable name. Let's take a look at that, and hopefully we can see a cross-section now. And we don't, because we have some type of error, so let's see what kind of mistake I made with that syntax. So something I did with that syntax. So F32. Oh yeah, so this is a define, so it doesn't actually have a data type. And since it's just a number without a decimal, it's going to default to an integer. So we need to cast that to F32. Well, it's not really a cast, it's a constructor, but, you know, similar concept, right? We just want to get it in the correct data format. Oh, nice. So we got something. We definitely got something, and that's kind of cool, right? So, you know, we could play with that, right? So we could do like dbg equals dbg times, I don't know, itime. Oh, we could just do dbg equals cos dbg. Now, cos itime, right? We want some type of looping value between 0 and 1, and then we'll just times it by dbg like that. All right, well, I just want to animate this and kind of see, you know, hey, what does that look like if the plane is like animating? And so that's kind of cool, where we're kind of like, and we can kind of see, oh, hey, that that ketchup color that we're seeing right there, that is the actual voxel volume. So we have the so the voxel volume, the voxel map is always going to be at origin 0, 0, 0 in our world coordinates. And our world coordinates are always going to be measured in fragment coordinates, which might be different than what you're used to. You're probably used to using normalized coordinates. But I think it's going to be easier to use kind of like pixel coordinates because we're thinking of this as like pixels in three-dimensional space. And so I want discrete pixel coordinates for when I'm trying to do things with them, right? So, right, it's going to be easier if we're trying to like load bitmaps into the voxels to like add texturing and whatnot. It's just going to be a lot easier if we do it this way. So this is really cool. So I'm pretty confident that our view plane is kind of like going through the voxel volume, right? Because we see that we have these two different magenta checker patterns, right? We got this light dark magenta pattern, which is for either an odd or even layer on the z, and then we have the lighter, which is either for an odd or even layer on the z, right? So we can definitely identify when we're on an odd or even layer. Now, the next part is I see that there's like this black, and the black kind of so that black is kind of that's not good. So why are we seeing black? So one idea is that that might be a very specific air color. I don't think it is. So what we'll do is, before we continue, and also we can see the colored regions, right? We can see, if we look at our tile map, let's look at our tile map data really quick. So if we look at the tile map data, the tile map that we kind of hard-coded here, we can see we've kind of like made this table surface, and some of these voxels are turned on, some of them are turned off. But right now we're not, I don't think we're coloring any of the voxels based on whether they are on or off. We're just trying to get a printout of if we are inside or outside of that voxel volume. So let's figure out, let's try to screenshot this and see if we can find why there might be, we're going to wait for that black section to show up, and we're going to try and... Okay, so with our snipping tool, we can take this region of the screen, and we're going to figure out what the exact color of this stripe is here, because that is a mistake. And so we're going to hope that this solid color here is a color we can identify in our list of error colors, so that we can figure out the exact piece of code that is responsible for this. So I really wish I had like a screen color picker app. So I'm gonna take some time and just screen color picker app. A minimal but complete color picker desktop app. Let's just give this a shot. Colorpicker.fr. So I'm gonna take this. I'm gonna see if this color picking app is suitable for my needs. Because right now what I'm doing is I'm kind of like screenshotting, and then I gotta save the file, and then I gotta open the file in Paint, and then I gotta like use the color picker there. And if we could just open up an application and instantly color pick from the screen, I think that we would have a better chance at, well, not a better chance. We would be able to debug quicker. So let's download this and see what we can figure out here. Okay, so they have a portable version on their GitHub, so that's awesome. And before I do this, I'm gonna make a note in my shortcuts here. I'm gonna say download portable color. Okay, so with that, and then I saw that I had a shortcut that was already called color picker, which makes sense because I probably messed with some code that did some color picking in the past. So let's see where we can find exact color picker shortcut. And we see paste CPD, paste JCPD, color picker dialog, and jQuery color picker. So, oh, this is new color picker. Find next. We want to figure out where exactly. Let's use match whole word only. Okay, so paste. Okay, so we have that, and so what we're gonna do is, since this is kind of getting a little bit big, we're gonna go over here. We're gonna take this, and we're just gonna design a prompt where we kind of like. We're going to reformat this into multiple lines because we're going to put the help file for this shortcut in an external file. And okay, and right, we'll have this like link for that, and from there, we'll also remember that we're going to need to take this exact phrase and color picker. We're going to remove this thing that says color picker. We're going to go up to the top of our shortcuts and color picker. And this way, when we say color picker, we can kind of get things related to the information we have touched previously, right? And because we're never going to remember these exact phrases, like download portable color picker. We might not remember that a few months from now. So to have these more general things so that we can route back to whatever we logged in our shortcuts will be helpful. So with this, we'll just say, do we want to open the file or do we want to paste the file? And usually I just like to open the file because we just want to open it for reference and see what our options are really quick. We don't want to clutter whatever we're working on with a whole bunch of text by like pasting it in there. So we'll take that and we'll do edit file because it'll open it up, so we'll see the options. And then we'll take this, and in our shortcut files we have a thing called prompts, and what is it related to? It's really miscellaneous. It looks like I used more for that. Prompts more, and there's not much in here, so we'll just do color. So we'll call it color picker. And actually, let's be consistent with our naming. Oh, I see why I did it like that. So I usually like all up. Oh, it's not gonna be. It's not gonna. Okay, so what we're going to do is we're going to rename this to, sometimes changing the case doesn't really persist, so we're just going to do cp._, and then open containing folder, and we're just going to remove that one that was called, oh, never mind, it's gone. Okay, so with this, we'll just put that in our shortcuts. So CP for color picker. We don't really care if we can identify this file name, just because this master shortcut kind of like tells us what's in our file system, which could be detrimental if we ever lose this, hence why I back it up twice a day to different repos. Because I have had this file be corrupted once, and it was a pain to like stitch back together and recover. Okay, yeah, sure, that works. And also, I would like to see this in a all underscore version, so in snake case, that is what it is. Okay. So continuing on, now that we know, where we are, now that we know where we're going to get this from, we're going to take the portable exe version, right? I just want a portable version. I don't want to have to install anything if I don't have to. And we'll go into our software folder. Don't worry about this. We'll put it in the exe folder because it's for actual running executables, not for installers. And we'll just call it color picker. And color picker portable.exe, we'll call it I'll call it cp23.exe for color picker 2 point whatever the hell. And run color picker, open color picker. And we'll take that, and we're saving it as this, so we'll take it like that, and run file. So, and then we'll also have in our prompts, right? We have different prompts, so we also need run color pick, runs color picker exe. And then over here we can do run color pick, and then run color pick and run color pick, like that. Okay. Okay, so now that we have that, we'll save cp23.exe. We'll save it. And, we've invested a decent chunk of time in recording this, so we're kind of like not hedging our bets, but we're kind of making a big bet here. We are assuming that this color picker is actually going to be decent, and it's going to do the job that we need to do. But all we need to do is be able to select from the screen and see the exact hex code of the color. Ideally, I would like to see more than just a hex code. I would like to see okay, so we have this color picker, cool, and let's see what we can do here. So pin to foreground, pick color. Okay, so we're gonna hit pick color. Okay. So it looks pretty good. And okay, so it's not giving any feedback when we hover over. Okay, so this looks like it might work, and it looks like it is all about whatever is in the center here, right? Yeah, yep, okay. So that color right there, okay, what is that color? 25025. So here's the thought. We have this color, and I don't know anywhere where I'm using, this is the those are the decimal values, and then there's the hex values, and it's like, I don't know anywhere where I'm doing that. So what is, if we take 25 divided by 255, if we take 25 divided by 255, we get 0.098. So it's not anything I'm familiar with here. It is a dark magenta though. It is a dark magenta. So I do like this app. I think that it's useful. I'll keep that around. But we have a dark magenta that is kind of showing up in our code, and that's just not that just does not seem like something we want. So the first step would be, well, we do know that we had some dark magenta in so in here we know that some of these are dark magentas, right? So really quick, to make absolutely sure that that stripe is, not that magenta isn't coming from here, right? We're gonna take all that and we're gonna edit that really quick, and we're gonna run it and see if okay, yeah. So notice that the well, no, that's not quite right, because we've made some of these have we made some of these colors the same now? Oh wait, you know what? I need to move this to a different monitor, or I need to change my monitor settings, because there's a checker pattern that I can't see that is definitely there. So if I need to calibrate my monitor really quick so I can see what's going on here, because there is obviously if we're gonna have to tone down the brightness probably. And that's not, we're losing some saturation. So it looks like the contrast, so I'm just toying with my monitor settings here. So the sharpness is very incremental. So you know what? I can't. It doesn't look like changing my calibration on my monitor is really gonna make this easier to find. Turn down the brightness. The brightness on my monitor really just looks like backlighting. So so that's not okay. So okay. So what I'm noticing here is that oh, yep, there it is. There is a solid green area. So it's kind of hard to see. But there is definitely a solid green. So what we're gonna do is we're gonna remove some of that and we're gonna figure out which one of these is the one that is giving us that solid green. And okay, so now we have, oh god, that's okay, yeah, we still have a solid green block of color that's showing up. It's very difficult to spot, but it's definitely in there. So we got to figure out which one of those greens it is, and it looks like it's the lighter of the greens. So if I do this in the code, I think I should still see a solid green block of color. So okay, so now our checker pattern is a little bit different, and I'm still expecting, oh, so I changed that one to, did not expect that to end up black. What the hell? Yeah, why am I ending up with black checkers? Okay, because 0.1 and 0 is pretty similar, so that's why that's why this is very close to black. So I'm thinking maybe we want to So it looks like it's this color. Or it's none of them, right? Optionally, it's none of them, right? It's still a black area. So we're saying it's that color, and if we... Yeah, I don't know if that's true, because if we change that to green, right? If that black color is what we think it is, then this will change it to green, right? So we have this, everything was green, and now we have a hard to spot green area. Yeah, okay, yeah, so it is this color right here that is causing our issues. So now that we kind of know that that is the issue, let's take this and let's take it and give it a different debugging color. So right now we have this kind of like we're making it kind of like way more intense than it needs to be. So I think one thing is this pretty much looks like black because it's so dark. Like if we take this and run it like this, it looks like black. Does it not look like black? Yeah, it looks kind of like black. And we can't really tell red, green, blue. It's very dark magenta. It looks kind of like black. I think we should probably up the... And then this brighter one, that's okay. So I almost say we want to take this and maybe we'll put this at like 0.25 and we'll put this at like 20 like that. And I think that might be a little bit better. So let's take that like that. And we just want to kind of fine tune this checker pattern so that when we're looking at it, we can kind of like visually confirm kind of like what we're looking at. Okay, so that's much better from my monitor where I can tell that I'm not looking at a black area. I can tell that I'm just looking at like a solid stripe. So now the question is it even possible to do that? If you warp through, if you're like, my thought is that when the volume is going in the wrong direction, that we're getting kind of this would be like a 0 for everything. Is there like an area where we don't get a checker pattern anymore? So that's my worry. Like it could just be that the slice plane is getting so distorted that that a solid block of color is resulting rather than a checker pattern. That could be it. Or it could be that like maybe in the negative space of our fragment coordinate values, when we're in like that negative space, we're getting everything truncated to 0, right? Because this color that's happening is 0. It's 0 out of everything, right? So that means, so that could definitely be because the x, y, and z coordinate, when it's not in a positive space, like when it's all negative values, could be just being truncated to 0 somehow. That could be the case. So to kind of like debug that, to kind of figure out how that is happening and what is happening, we can change how our slice plane is animating and see if we can get some other useful feedback from that animation of the slice plane that makes sense. So right now we're kind of like doing it like this. Well, what if we just change the H value on all of them, right? So now the plane will just move up and down. And now what we should see is we should just see the colors kind of like pop to different colors, like for all, right? Well, you'll see. So, right, we have this color and then pop, 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 right? Because we're just going through these different layers. And what I notice, pop, 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 right? We're seeing one of those layers is just a solid magenta, right? So it's that 0 for everything color, right? So that tells me something. Now, before we get any further here, and before we start debugging this a little bit more, I want to make sure that I can find the colors within here as. So this is nice and all, but the problem with this is these colors. We had to do we had to do a lot of thinking to figure out, are these the actual colors? Are these the colors we're looking for? So it would be nice if we could supply a hex value, right? And if we could put hex values in the actual color source code, and then when we use the color picker on the monitor, we could see the actual hex codes, right? We just control F for the hex code and we can just find it, right? Because there's no hex code here. We had to like look at this and kind of like extrapolate where that was coming from. If we could just color pick onto the monitor, get us unique hex code, and then be able to find it in our source code, we would save ourselves some debugging time. So we should probably try to figure out how that is done. And so hold on. Okay, so we need to. It would be much better if we could get hex values into our source code to help this process. So the first question is, can we use hexadecimal in GLSL? And the quickest way to find that out is, I could Google it, or I could just look it, or I could just do it, right? So I could do uint hexadec equals 0x R, G, B, and A, right? That's kind of what we want. And we just want to see, like, if we just throw that in there, does that actually compile, right? If that compiles, we're good, and we can work from there. But that tells me no nos. So can it convert from const int to high p uint? So you're telling me that this is an integer, huh? Okay, so I would never think of this as a signed value, but the debugging message kind of uint. The debugging message I got from this is kind of telling me that this is supposed to be like that, because this is somehow natively, without any context around it, it is a signed integer. Kind of like without any context besides this, we just assume it is a float. And right here, that we assume that is an integer, right? So let's take that, we'll paste it, let's see if that runs. Okay, so that runs. So when we do our hexadecimals, we need to do it like this. So the first thing I want to do really quick is put that in my notes. So GLSL hex. And we'll just take that little snippet so that we have like a little reference for how that's done. So what I would like is to take what we have here, and I think we have. It's nice that we could create like this table of colors like this, and that's all nice and whatnot. But it'd be much better if we could. Now the problem with this is if we there's some extra processing power involved with doing it like this. Like if we put hexadecimal values into the code, we have to parse it, right? We have to huh. Uh hexadecimal to RGB values in WebGL shader. WebGL shaders can't perform bitwise shifts. That might not be true for newer versions of GLSL. Okay, so what we're going to do is we just need to, we don't need the actual, we just need that number in the source code. We don't actually, it doesn't matter where it is though. So what we're going to do is we're going to do like a, it was, so v4, so it's a vector, and, well, let's take, okay, you know what, let's just painstakingly figure out what all these colors are, and then, yeah, let's just do that. So we're going to painstakingly figure out what all these colors are, but then after that, we can't really change them, because if we change them, it will no longer, God, that kind of sucks. Yeah, I mean, that's the best way we got. We're just gonna have to not change it. Do we have colors that we like? Do we like this system? Like, we got these ketchup kind of colors, and I don't like how one is like a ketchup color and then the other one is like, so one is a ketchup color, so it's bright on dark, and then we have a dark on bright. Or do we? God, it's moving a little bit fast for me. So let's change the eye time really quick. So I'm gonna put a breakpoint here so I can find this later. And we don't need that. We're good. We understand. But for this eye time, we're gonna do like eye time divided by I don't know. I think if we divide it like that, it'll be slow enough to where I can kind of see what's going on a little bit better. Okay, so going a little bit slower. Okay, so light on dark, and then dark on light. So I kind of like that contrast because it's kind of like easy to know where we are and whatnot. Huh. However, I think with out of bounds voxels, I think I would really like those just to be gray, because, yeah. So let's just change. If we're gonna have to commit to what these colors are, we're gonna have to make a little bit more decisions on this. So we have this. We have dark checkers and light checkers is really what I want. So we're gonna take these G's and we're gonna put those there. We're going to put W's here. So we're going to get rid of the magenta and just make it grayscale. And run that. Let's see what that looks like. Okay, so now we got these grayscales. And that just tells us that when we're in this gray area, we are like out of the voxel bounds. If we see gray checkers, we know we're outside of the bounds. And if we see that the checkers are kind of dark, we know that we're in one area. And if they're light, we know we're in another area. Now we might want to make this a little bit less contrasty, but not too contrasty, just so that, because right now the cross sections laid on top of each other might blend together. where with the light checkers, the dark color from the light checkers might mesh with the light color from the dark checkers, right? So we don't want any cross pollination between these two checkered gradients. We want two distinct checkered gradients. So if we have too much contrast between these two checkered gradients of gray, then they could merge together when we look at them. When we look at like the different strata, right? When we look at instead of looking straight down on it, right now we're looking into the Z. But if we were looking from a view where we are, if we're looking at like the YZ plane or the XZ plane, and looking at the different strata of voxel layers, we might still see a checker pattern where we actually want to see like a layered striping pattern. And so we need a good value hierarchy to achieve that. So let's clamp the checkered values we have a little bit more. So right now we have like 20 and 25. Let's clamp that to like 20 and 21. I just want to see what the difference of like what does one value make in there. Okay, so that's a little bit too a little bit not contrasty enough. So let's use one more value and see what that looks like. Okay, so I like that. And then for the light checkers, we have like this 0.9. So we're going to do like 90 and 0.91 like that, right? And actually what we're going to do is to make this a little bit easier. Well, let's just do that first. Let's make sure we know what that looks like. And so we got dark checkers and we got light checkers. The light checkers actually need a little bit more contrast. Well, actually, yeah, because we didn't use two. Okay, let's look at that, see if we like this. Light checkers, dark checkers. Light checkers, dark checkers. Light. Okay, so I like that. I honestly want to pump it up just a little bit more depending on what my monitor looks like. Can we just do 5s? Like, is that too much, or is that back where we started? Let's just take a look at that, see what that looks like. So yeah, I can definitely see more values when it's darker. And because I can see more values when it's darker, I think that should be clamped a little bit more. So for the dark checkers, we can do like, we just need those 2 points, like that. And now let's take a look at that and see if that is kind of like a suitable checker value. Okay, so we got this checker value. We got that checker value. This checker value, that checker value. And okay, sure, that's good. I like that. And then might not be perfect, but we're gonna have to change this anyways because we need for these different intensities, we need to so if we do like 0.2 times 255, that is like 51. Okay, so what we're gonna do is we're gonna do like 51, and then 51 to hex is, what is it? 0x33. So this is F32 0x33 divided by 255. Let's just divide it by m. Okay, so if we take that and we put it in here, see if we made any syntax mistakes. And okay, so that still works. And do we have have we maintained the checkering colors? So we have these dark gray checkers, we got these light checkers. So okay, so now we're gonna take 0.22 times 255, and what do we get? We get 56.1. So let's take 56 to hex and see what that gets us. And we get 0x38. So we're going to take F32, 0x38 divided by m. And let's just keep on going for everything, right? So we got the idea. So 0.9 times 255, 229.5. So we're going to take 229 to hex, and 0x5e. So F32. And the reason why we want to use actual hex codes is because we want it to be easier to find like the color in the source code by color picking from the screen, and then like control Fing for these different values. And this will definitely help us. So it's not as good as being able to look for an exact hex code, but this is a start. So let's take this one, and so 0.95 times 255, and that's 242 with some decimal places. 242 to hex, and we got 0xf2. So we'll take that and we'll do f32 for a float 32, and then we'll divide by m. And with that, we've converted every... Oh, wait, we have I as well. I don't know if I really like these colors yet. I like the gray, so let's just run this, make sure that still is correct, still running, and still looks how we expect it to look. All right, so it recompiled all right. And we got the gray checkers and the light gray checkers. So we got those two different layers of checkers. So what I think for the interior voxel volume, I think it would just be better to set it to like a green checker value. So we can use the same kind of checkering that we've been using, but we can just make it green, right? So what I think would be better is these eyes. Let's just get rid of these eyes, because these are like more variables that we have to keep track of anyways, and I don't want to. And then over here where we're doing this, I'm going to blank these all out first, right? So I'm going to blank them out so I can just think about what we're doing. And I know that I just want some green checkers, right? And I know that I want the light green checkers and I want the dark green checkers. And do we want to do it like inverted, or do we want to do it like with the same layer? I think it makes sense to have it the same, so that on the even layers we have the dark checkering, and then on the odd layers we have the light checkering, and it could be either gray checkering or green checkering, depending on if we are inside the voxel volume or not. So with that, I'm just going to take these letters and use them in the correct place. So RG. So we're going to take the G channels, and we're just going to put that, we can just paste it like this. So we're going to take the G channels, and we're just going to move them down here. And so now we're going to expect to see the same thing as we saw earlier, but now we'll see green for inside the voxel volume. So let's run that. Okay, so that looks much better, right? And that, it looks much cleaner, looks much nicer. And we're just going to have to remember the convention of, you know, what does that green checkering mean, right? And the green checkering means that we're inside the voxel volume. And we still have that solid gray, which we got to figure out. I think it's just because the camera is going into the negative space. I think that's what that is. So we have to think about how is our math working. Well, first of all, before we go that far, let's I'm gonna find the color picker. that first I'm going to try to reload my shortcuts, but for now I'm going to find the color picker application that I downloaded, and we're going to see if we can get the exact hex codes off of the screen now, and if they reflect the hex codes that like are in the source code, right? So so in my color picker folder, I'm going to just run the color picker app. And I think last time it popped, it seems to take a while to start up, which is kind of like, I'm not too much of a fan of how long the color picker is taking to start up, but it's still faster than me. It's still faster than what would happen if I tried to save a file, open it up in Paint, and then do the color picker. So let's do this, and let's just right now any of the colors on screen should be colors that'll show up. So let's try one of these green values, and we have 56, and we see 003800, right? And if we look at our code, we definitely have a 38 right there. So let's just do some more color picking and see if every time we color pick that we get a color that is actually in our code. So color picking again, we see 3 3s, we see all 3s, and we have this dark gray right here, and that's all 3s as well. So with that, what we could do in our code is we could try to there's 255 different colors we could use, right? So we could try to that would be 255 possible colors that we could output to the screen to give us some information. However, it'd be better if we could find the exact hex codes. So what we're going to do now is we're going to refactor this just a little bit. So we're going to take, hold on, mod math. Hold on. So I have a shortcut called F mod math. So this needs to be fixed around a bit. Okay, I don't have... I'll worry about that later, the next time I have to do this. Okay, so let's refactor. So we're going to take these different colors here, and we want to refactor in a way where we can kind of know that the code doesn't lie to us, and that changes to the code won't end up lying to us later. We hope not to change these values, but if they change, we don't want any problems. So what we're gonna do is we're gonna do like underscore 0x 333333 and like that. We'll call that vector 4, and we'll set it equal to a vector 4, and we'll set it equal to this, right? And it's like I'm not set on that being kind of like the best way to do this, but let's go through them in order. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 of them. and we'll just kind of go through all of the colors, right? So we can just take them and we will paste them down where they belong. So this is the fourth one, and then we have this one. Okay, so now that we have pasted those all, we want to make we want to quickly check that we've kind of like refactored this correctly. So we'll kind of do that and use this kind of token highlighting to make sure that everything is the ones we think they are, right? Okay, so that is correct. So we know that they are matches. The next part is obviously these variable names need to be changed. So we know that the G is the 33, and we know that the capital G's is the 38s, right? So we do 38, 38, 38, right? And then for the white, it's an E5, right? So the dark white is an E5, if that makes sense, dark white. So those are E5s, and the light whites are F2s, right? So we can take those and go F2 over here, F2, F2, F2. And then for this stuff here, it's exactly the same, right? We were very consistent in how we did things, right? So we have G, G, W, W, and we also have G, G, W, W in the exact same intensity levels. So what we can do is we can just take these and we can go zero it out, and then we know that alpha channel we're not paying attention to right now. We're just looking at the RGB values, and we just want to take these colors and plug them in where they belong. So we can take this middle section of hex values and we can just put it right down there, and bam, we got all the correct colors, right? So now that we have those correct colors, we can take them and paste them into where they're used in the code, right? So originally we kind of like declared them where they were used, and that was actually very helpful, right? It was very helpful to do this first and kind of build up to where we are, because we were changing and tweaking those values as we were working with them. And now we kind of have to commit to the values we've chosen and just plug them into the space, right? And it's easy for me to remember where they go because I ordered everything by index, so I can easily know where everything needs to paste, right? The more uniform you are, the less you have to remember and mentally juggle. So we've condensed that code a little bit, and we might want to move this over, move that over. Yeah, I mean, that's good enough for me. So now the idea is, for these colors, I don't want these hex colors to be declared anywhere else in the code because they're used for this voxel checkering, right? And I want it to be where if I'm looking for a certain color in that source code, I just want to be able to find it by color picking and then control Fing. So let's run this. So it's still running. So let me copy it all and paste it again, just to make sure that the right thing was on my clipboard because I'm paranoid. Okay, so that's still on my clipboard. I mean, that's still working. It's still working. So let's use the color picker and just color pick something. So let's it doesn't really matter what it is, but yeah, let's just color pick. And we see E5, 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 right? And so if we were to go control F for E5, 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 right? Oh, okay. So we're not finding anything. So hold on. Okay. So if we control F for those E5s, we find them right exactly where they are used, right? So now we have a way to connect the code on the screen, those pixels on the screen. When we find these odd pixel artifacts, we're going to have a way where if we just open up a color picker, right? We open up that color picker and we pick from the screen. Let's try to get some of that green this time. So let's wait for that green to show up. Okay, so if we just color pick some of that green, we see 003800, right? And if we control F, 0038000, find next, and we find exactly in the spot that it's used, right? So we have this direct connection of the what is on the screen in the shader and where exactly that is in the code. That's very important because that can be really hard to figure out sometimes. So we've done a good job here figuring that out. And since we're kind of like in this train of thought, it might be good to take this like convention of how we're doing this and kind of take it over to this other function that also requires that we know exactly what we're doing. And we have this, we kind of like started to kind of do that, but not quite. So we have, right, because we have 32, right? So this is a good start here. We have a table of errors, and we have these different colors, and 32 is the decimal value, so we'd have to know what like 32 is in hex, right? We want to be consistent, right? Like if we're going to use hex codes for everything, then we want to, we can't just use decimal some places and hex in other places, right? If we're going to make it easy to like use the color picker and search for where that color is coming from, we want to stick to one thing. I would like to stick to hex. So 32 to hex, what is that in, so it's 0x20 in hex. So how are we going to do this? Okay, it doesn't really matter too much where we put it. It's just let's just put it here for now. And we have did we do a 0x or did we just do like did we do it like that? I hope we did it like that because that's going to be easier to find. Yeah, so we did the 0x prefix, so we know that the variable is for a hexadecimal number. So that's good. So 0x, and we'll use 20, 20, 20. Actually, we don't have anything that's 20, 20, 20, do we? We have...
Okay. Love you. Take care of yourself. Call when you can. Okay. Bye.
So 0x, 20, 20. Huh?
Frankie might have to stay longer.
Okay.
I just talked to them, and only because they might not be able to get their insulin.
Uh-huh.
So they're already like know how to use the glucometer, know how to inject themselves.
Uh-huh.
Have talked to a dietitian.
Yeah.
You are not monitoring Facebook.
No, I'm not, because my Facebook blocker goes off after 15 minutes.
My phone. You have my phone though.
Yeah. I am recording stuff. Like
Okay.
I'm trying to.
It doesn't matter. I just talked to Frankie.
Okay.
I didn't specifically ask.
Insulin normally type 1.
Normally, but type 2 can be insulin too, and at 25 would be really, it doesn't make sense that it was type 1. I mean, we'll find out more. They may be coming home in like an hour or something though too.
Okay.
They don't know whether the insulin's available. So Jamie,
Uh-huh.
they also need underwear and pants, and they need laundry done.
Okay.
So, you need to go do. Frankie prefers the pronoun they, and I try to respect that. I know that can be confusing, but I try to respect it. So, you need to do laundry like now in case they're ready to go in an hour.
Okay.
Yeah, I think that's everything. To talk to the dietitian, have a meal plan. You know, basically low carbs, just what bars used to eat. Injecting themselves is no problem.